Interesting. I have one. Laura up here, okay. Why is that little black?
What is it?
No, okay. That one, okay, you can. It's not, okay, well, very good, thank you. So I'm going to talk about marine seismic and offshore drilling, but of course, partly what we'll talk about also is volcanism and volcanic processes. And this is just a picture I took in Iceland a few years ago, just at the Fagradalsfjall eruption. So I'm saying, like, if any of you want to, I mean, Iceland is a perfect place to study basaltic volcanism, and with the current activity, I mean, it's just amazing the type of closeness. You can go really close to the eruption centers, and it's really something to see if you have the possibility. Of course, Hawaii is another favorite place to go to study these sort of natural phenomena of volcanism. But I'll start with just a little bit of overview of this PADBAS project, or what we want to do in terms of storing CO2 in offshore basalts. And it's just a cartoon here on the right side that is motivated from previous work that we've been doing on the mid-Norwegian continental margin, where I started my PhD working on this IODP borehole 642E, which was drilled in 1985, and at that time, my supervisor, he just came back because he was a co-chief of this drilling rig. And I was just going to work a little bit on these wireline logs from this borehole. The drill basically poured 1 kilometer of basalts, and for some reason I continued to have this as a project going on for the next the rest part of my career in this way. So we have this very famous type of borehole on the Norwegian margin that drills into the federation of these SDRs, so seaward dipping reflectors, which can be very variable in composition. So we have massive cores of basalt flows, but also quite vesicular and porous flow tops. And that this could be a place to store CO2 in these basalt sequences. Basically, in the 642, it's more than 100 individual lava flows that were penetrated. But there's also sedimentary successions below the basalts, and we know that the very large volumes of basalt mappable in 3D seismic data in the Northeast Atlantic. There could be a potential for permanent sequestration as carbonate if the CO2 reacts with the basalts. We have some marine shales as an extra seal in the overburdens. In this case, we can also inject supercritical CO2 at seabed because of the water depth is about 1,200 meters. Plenty of access to salt water. We can do leakage monitoring in the sediments by using like P-cable, for instance, repeat surveys, and it's very far away from human activities. There are many concerns when it comes to of course, to do CO2 sequestration, like access to CO2. They just opened a new reservoir in Norway, a saline reservoir in Norway now, but they're still waiting for the CO2 to come. So of course, somebody needs to provide the CO2. We're always concerned about the reservoir permeability and injectivity. So that's, of course, what we talk about here too. Is it really possible to inject CO2 in sufficient volumes to have a meaningful effect on the global climate? That's a big question. What are the reaction rates and clogging if we don't deal with geothermal areas, but we are in the sort of cold water area, perhaps dominated by salt waters, and of course all of the engineering and cost. But for us, it's really the geological problems that we are concerned with and that we work with. And our goal really with this project is to develop 1 to 2 pilot sites for CO2 injection in basalt by 2 years. So just small scale pilots, most likely onshore and hopefully on the Faroe Islands. We have then the basic financing for the research and development. but clearly we need an industry support to realize a pilot. So that's also a part of where we want to go and what we are discussing. So this is sort of the summary of the talk, I guess, and what we are doing. So I'm just starting with that. For me, it started in 2014. You had this beautiful other eruption in Iceland, the Holaran eruption, one of the larger historic eruptions, was more than or moving towards 1 cubic kilometer of magma. And we were in Iceland working on outcrop data, but we also had the chance to get the helicopter and fly in there. And with Sigurd Gislevsson, that is the inventor of the Carbfix, and he basically told us about them that they have this concept that they try to put the mix CO2 and water and inject it into permeable basaltic rocks and then do carbonatization. And he's a sort of a geochemist and worked with Morgan Jones, that is at that time was a postdoc at the University of Oslo, and he spent quite a lot of time with Siggy on Iceland on this part. And that was sort of what's been leading up to the Carbfix project, with interaction with Lamont, particularly, and geologists from there. So this is a recent sort of a synthesis here on global carbon capture and storage in basaltic rocks by Eric Olkers and Siggy, then that was just published last year. So they made a lot of progress over these 10 years. And basically this is the Carbfix injection well, as it was two years ago. It's a helicided geothermal plant. Basically in this, if you go into here, they just mix the CO2 and water, so it becomes like soda water. They pump it into the injection well, and then they even have a museum there at the power plant to show how all of this is supposed to work in the way that you get carbonates in the basalts. Yeah, so this is sort of also partly our motivation then for this PERBAS project, which has sort of the title Permanent Sequestration of Gigatons of CO2 in Continental Margin Basalt Deposits. And it's funded by this ACT, so Accelerating CCS Technologies. It's phase 4, and it's one of these very awkward international programs because it's Norway, and then it's Germany, and it's India, and it's the US. So it's a quite mixed group of companies and nations. So it's headed by GEMAR in Germany. And then you have a TEEC as a geophysical company in Germany, 3 sort of research institutes in India. And then IFE, which is Institute for Energy Research in Norway, outside Oslo, University of Tromsø, and Weber as a company, and then you guys and Colorado Schools of Mine in the US. So it's been quite interesting just to get the proposal together and get it funded and get agreements and so on, but we're there. It's quite nice. We have quite a few other type of projects in Oslo. Working on a related project. We started with some master students at the University of Oslo that published 2 theses on this in 2021, and then internal project with University of Oslo with PhD students. So Maria here, she continued on the PhDs, also a few postdocs, mainly physicists and so on, that working on carbonatization and atomic scale modeling of carbonatization reactions. So that runs up to 2026, called CO2 basalts. We had an internal research project in Weber from 2020 to 2023. That's what's called basalt CO2 sequestration. So it's a bit of activity, but it was also partly a motivation for the drilling. So I'm going to say a little bit about this scientific ocean drilling and IDP Expedition 396. And I'm doing a few lectures on this as a part of the ECOR Distinguished Lecture Program. So I'm putting up a few slides here just in the beginning to say something about the scientific drilling that started in the US in let's say the late 50s, early 60s with the Mohawk project. Then it moved on to this very highly successful deep sea drilling project that lasted for almost 15 years. That drilled the world's oceans. Was really the first big program to collect samples from all the world oceans. And then it went into this ocean drilling program with a new vessel from 1985, and it started its then drilling on the Norwegian margin, where I got involved with it quite early on. And I've basically been involved with the ODP projects ever since, in different aspects, writing proposals, going to sea. I went to drill the Greenland margin with, or participated on that in the 90s, and we almost sank the ship. But that's another story. It was the least successful drilling operations ever. We got 100 meters of core or something like that for a 2 months expedition. But then the ship was for a long time in the Pacific Ocean and far away from the Atlantic. We wrote some proposals. We never got it to go to the Atlantic, except that a few years ago, we realized it would come back before the end of the program, and we rewrote the proposal and were successful and got the ship. Unfortunately, the program, as we know it, will end at the end of the year. So the ship is probably being scrapped. It could have continued, but there are some issues with who's going to fund it and many things. So it continues as a IODP cubed, but they don't have a drilling vessel, so it will, and they don't have a lot of money, so activity here will go down a lot in the near future.
Can I ask a question regarding the previous slide?
Yeah.
So you have the arrows for the scientific drilling on shore and IODP approaching each other again. So are they going to be related again, or?
Possibly. I mean, there's the interaction between, they also have potential for joint projects, we drill onshore or offshore between ICDP and IODP. So we're working on proposals for that too. But IODP is a fantastic project in the way that everything was funded when you go on the sea. ICDP, you get just partly funded, and you need to find the drilling operator, and you need to find extra money. Highly complex operational thing. This, when we went from Iceland in 2021, we go to the Norwegian margin. We drilled something like 10 different sites and 20 holes in the 2 months period. And for some reason, the weather was like this, it was calm sea, August, September. I mean, that can be quite rough. I mean, we were thinking perhaps we could have a lot of downtime. We had one downtime because of weather. So quite highly spectacular. And that's, of course, at that time, it was during COVID. It was barely touch and go to get out there. You had to be in the quarantine before we went. We had to say with a reduced staff, but still it's a lot of people and a lot of experienced people there in this group.
And no masks. No masks.
No masks.
That's because you get thrown out.
No, I understand that.
Well, we were wearing masks for the first week, and then you throw them into the sea. Because, I mean, if it was COVID there at that time, I mean, it would move around anyway. So that was totally fine. So overall objectives is really determining the origin of large igneous provinces, like melting in the mantle and how you do melt from the mantle into the crust and into and form then a new oceanic new oceans, so understanding the birth of an ocean. But also what we are very interested in is to understand the impact of these large igneous provinces on mass extinctions, global warming, but also CO2 sequestration as a secondary objective. So this is sort of the area that we studied when Europe and Greenland broke apart some 56 million years ago. We had the formation of this large igneous province, and we find a lot of volcanic deposits on both sides of the Northeast Atlantic. So on the Vøring margin, we find these very classic seaward dipping reflectors. So these are the type examples of of the most characteristic features of volcanic margins. We find them also going down along the mid-Norwegian margin, the Møre. You find it on the Faroes and the West of Shetland basins and the Hatton Bank and in and the Rockall Plateau. So it's the whole margin here is characterized by these very voluminous breakup volcanic complexes, and you find it also on the conjugate Greenland, eastern Greenland margin. So in the upper part here, but also SDRs on the southeast Greenland margin, and the Iceland is sort of the remains of this large igneous province. It's the only place where you have sidereal seafloor spreading in the entire world. And the whole area is anomalous shallow because of the heat from this Icelandic plume. And several drilling legs been devoting to understanding these volcanic rifted margins. So it then started on the Vøring in the 70s and on the Rockall, and then they went back in the 80s to drill the Vøring again, and then in the 90s to drill the southeast Greenland margin. So it's been up to about mid-90s. So it was a lot of work that was done on characterizing this.
What was the light blue going across from?
I wanted to ask, yeah.
Which?
Light blue
blue,
through
right?
Iceland.
Because it's a large ridge. It's basically the Greenland, Iceland, Faroes ridge, which is a very massive bathymetric feature. So it's voluminous volcanism connecting Greenland to the Faroes.
Okay.
Whereas you have in the yellow here, you have more like normal oceanic crust and spreading center. We also have this microcontinent Jan Mayen out here in the middle of the ocean, which is yeah.
Yeah. So what's the red spot? Because that's where my field area was at the scare.
Here?
No.
Okay, here, yeah. So these would be more these intrusive complexes, you know, like the like down here when you have the Skergård here, yeah, it's
so the red is the okay. So
it's igneous.
So there must be large ones all under that ridge, right?
Yes, but we don't know much about what's going on.
Interesting. I never thought much about the ridge
because on so much geology that's hidden below these sort of simple polygons with fixed colors. Yeah. So the red circles here are igneous.
Yeah, it's like Illy Masa, Skergård.
So then, of course, for us, it's like, but since the 90s, we got a lot of new seismic data, we got a lot of new IDs, basically. So that was really our motivations to write the new proposals to collect more data in these parts. So basically, we had a workshop in Germany, then also writing the pre-proposals, and it all went quite quickly because we did the workshop in 2018, then write the proposal in 2019, then the prospectus in 21, and then because of the COVID, we managed to get out there. We got access to the ship. They didn't want to sail in Antarctica or something, but then closer to Europe, I think. So it all happened within 5-6 years from having the workshops to finishing the proceedings. But of course, it builds on previous proposals that were not so successful. Then going up to Iceland in 21. This is during the Fagradalsfjall eruption. So here we have this Enantiolone type of volcanic system, different segments, as you know now. So this is what we've been talking about previously today. You have this village here, Grindavik, and up here you have what's called the Blue Lagoon and a geothermal plant that's called Svartsengi. And here you have inflation of magma in the sill below this area, and then you get the eruption going along dikes some tens of kilometers away. So you have lateral transfer of magma, it comes out. And the big scare was, of course, that the eruption was going to go on in the city itself and destroy the city. It's a wealthy fishing community here because previous eruptions been going into the sea, creating very beautiful harbor, safe harbor, so. So you sit in the middle of the spreading reef basically out there. And it's like, yeah, like you said, it's amazingly nice to go up and see these type of eruptions, and on Iceland you can get quite close and see things. Okay, so but we were sailing then off to the Norwegian margin, and this is an oblique view where you see the north is to the left. It's a bit difficult to point here, perhaps I could make Teresa point to. No?
Yeah, it's a laser.
Huh? You see it? Yeah, okay. Yeah, so you have that. Yeah. So basically this is a Norwegian channel in the North Sea with lots of oil fields, but we are basically working out on this continental margin, so the Vøring Plateau are here. And over the years, then the industry's been collecting quite a few 3D surveys in the deep water areas where you also have basalt. So this white polygon here is a large survey, but more recently TGS been collecting something like 40,000 square kilometers of 3D data, which also cover quite a bit of the basaltic influence domains. So we've been able to use this data to optimize drilling targets. I'll just show you a schematic profile across the margin. So this is basically showing the SDR sequence, so up to 6 kilometers thick basalt flows that have been previously drilled. On the seaward termination, we find outer high that we postulated to be emergent volcanoes before we go into oceanic crust without the receiver dipping reflectors. On the landward side, we have what we call landward flows and a lava delta. So the prograding volcaniclastic sediments where you go into the sedimentary basins with where we also find then a lot of sill intrusions and associated hydrothermal vents.
So once again, if we go back to the previous map,
yeah,
can we go to the previous slide just really quickly?
Yeah. Okay.
Here. Mm-hmm. So you say landward. Where's landward?
Towards Norway.
Okay, not paleo landward. Or...
No, so it's towards the continent.
Okay.
And oceanward, so it's ocean basins to the left there. Okay.
They seem to be going like parallel.
But this is a bit like also a schematic profile, you know. So we interpolate the drilling sites into the locations where they were. So let's start to talk about the sills and the vents and the PTM, the Paleocene Eocene thermal maximum. And if you look at these sort of paleo temperature records, that's been based on oxygen isotope data and so on. We see that we in the Paleocene and Eocene, we had a much warmer temperature than today. It's up to like 12 to 14 degrees warmer than in the early Eocene hothouse. Then you had this more or less long-term cooling before we go into current day sort of icehouse conditions. And then you have here some of the sort of projected scenarios for future global warming when we might move back to some of these sort of hot house or warm house conditions that we had in the Paleogene times. But we are particularly interested in this spike here. So it's a brown spike here where we have 4-degree warming over a period of 100,000 years or so, where the temperature was 4 to 6 degrees warmer than the hothouse conditions. And this is called the Paleocene Eocene thermal maximum. It was the warmest period during the last 66 million years, and it was likely triggered by a release of something like 2 to 12 teratons of carbon gases, greenhouse gases. So in 2004, we published this hypothesis in Nature, where we used 3D and 2D seismic data to map out these sort of vent complexes, so pipe-like structures connecting sill intrusions with the paleo surface. So basically, this cartoon here shows sills that's been intruded into sedimentary basins, heating organic rich rocks, forming greenhouse gases, creating overpressure, then punctuating the sediments and transporting the greenhouse gases from the sediments into the hydrosphere and into the atmosphere. And this for us has been something like a hypothesis we want to test in some ways by drilling and by observations. It's mainly based on seismic data, but also some analog data from other places in the world. But it was a motivating factor for us. So basically what we think happened, you have the sedimentary basins, you inject magma, form these extensive sill complexes. They're typically saucer-shaped in the shallow subsurface. You heat up the aureole rocks and you form greenhouse gases, and they're being injected, and you trigger global warming. You can also try and get other type of elements in, like mercury and perhaps other poisonous elements that could trigger global warming. So I'll show you just some examples of what it looks like from the seismic data. So this is the paleo horizon as it's mapped out today on the 3D cube. I'm going to look at first this infinity sill here, and then afterwards the Mudgun vent. But we mapped more than 1,000 of these hydrothermal vent complexes over the years. It can be up to 10 kilometers in diameter, so quite extensive.
The whole region.
Hmm?
The whole region, 10 kilometers, or each one?
Well, each one of them can be, they can be from, let's say, a few hundred meters up to 10 kilometers in diameter.
Wow.
Typically, they're like 1 to 2 kilometers, these vents. So the seismic data, it looks something like this. So here you see a high amplitude reflection, which we interpret to be a sill. It typically have these sort of transgressive segments. And you can see above it, you got the stirred seismic, and it ends up at the paleo surface here, and these sort of eye-shaped features that is vent complex itself.
So, and on the right, we have two similar things, which
We have some similar ones here,
same.
yeah. And you can see a few of them here. So
That's
what we do
exactly
is,
where you expect them to.
Yeah.
All of those things right on the corners.
well, we can map out the sill here. So this part is a nice saucer shape. It probably comes here. We have a student that works on this now with some sort of bridges. But what you see here is that when you map out the paleo surface, like you see, just as you say, I mean, most of these pipe structures, they're located at the termination of the sills where it bends upwards.
So what was the resolution of your seismic cube for that?
This is conventional seismic.
Okay, so
So it will typically be, let's say, with 25 or 12.5 meter bin spacing.
bin spacing, but the source, the usable frequency would be.
Well, it's a typical dominant 30 hertz or something, 30, 40 hertz is a dominant frequency.
So this is like 150 kilometer sill or something.
Yeah, I mean, they're not, you see the scale here in some ways, but 50 kilometers or something, this is a fairly small one.
That's a pretty good size sill.
But I mean, this, and if you see like here is another one, then again, this is a sill complex as we map it on 2D data previously. So the scale down here is 10 kilometers. So, I mean, these sill complexes are large. I mean, a large igneous province. This volcan is
it's a complex of multiple sills.
Yeah, and they connected, and they're much larger than anything human or we had experienced in the last 50 million years. I mean, this is gigantic eruptions.
And how thick are those individual sills, do you think?
So here we have, this we drilled, well, not we, but the petroleum companies.
Yeah.
So here it's 90 meter thick. Here it ended up in a 50 meter thick sill. So you can see the wireline logs here. You have this very large increase in velocity. So from 3 to 6 or 7 kilometers per second in a box-like response. But we also see that you have increasing velocity in the sediments towards the sill and decreasing below. So it's a metamorphic aureole that you increase the velocity because of the thermal effects. So this we can also map out in the 3D sense. But what's good here is like here you have a well that drills the sill and the oriole. Here it drills the same stratigraphy but away from the sill. So you have a calibration also. In this case, we can compare the maturation, for instance, the vitrinite reflections. This is a basin-wide trend, but here we see that you have it in the intruded borehole, so you get very, very high vitrinite reflectance moving towards the sill. But also between these two sills, you also get an increased maturation. So you have a decrease also in TOC, but you got increased maturation, decreased CO2 in these orioles. This we can model then, or not we, but this is geomodeling solutions. So some of our colleagues are developing a lot of software in a way of how you get heat up the rocks, how you can generate methane or hydrocarbons, how you get pressure buildup, and how you get migration of these type of fluids towards the subsurface, and how you basically fracture it over the.
And what is the color scale on the right, the bottom?
Here?
Yeah.
I think it's kilograms per cubic meter for a 1 meter thick, very thin type of. It's a little bit like a random scale, but you need some third dimension. It's a 2-dimensional model, but it's partly three-dimensional.
And geomodeling solutions, who they are? Who are they? Geomodeling solution.
Kartik Iyer, Yuri Podachukov was there, and Dani Schmidt. It's this ETH group basically that modeled it.
Podlachikov was Yuri
was
Okay.
And
I thought that it was like one of the compaction models.
It's mainly Dani Schmidt. He's Swiss, but he lives in Norway. Kartik Iyer lives in Germany. Lars Rübke is also a part of this, but they're sort of in this environment that they've been developing this 1D, 2D, and 3D. Part of it is also freeware, and that's CD1D.
So is that plotting CO2 that methane that's left that area or that's accumulated in that area, or?
Yeah, so this is also what it, so I'm not going through this in detail, but some of it is vented, some of it will be remaining, in the host rock. So definitely not everything is transported away, and of course, if you have advection or convection or conduction only, and so on there quickly becomes a lot of complexities involved in the modeling, and these models. I mean, if you do it in a simple case with fluid conduction, you can do it quite quick. When you have all of this sort of convection transport and so on, it takes only days to do a model.
The grading has to be really fine to capture the pipe structures.
Yeah, so quickly it can become very time consuming to do some of this modeling, and to do the fracture modeling and things like that.
And what's the time scale? Oh, 9,000 years. Okay.
It's not, it goes quite, this is 9,000 years. So I mean, the time scales are short, but at least it gives you some estimates on the amount of hydrocarbons you can generate. Of course, you need to know the initial conditions in terms of how much organic carbon, what was the temperatures, and so on.
So is that one sill, or it must be multiple sills?
So this is also, this is up to you as a user to decide.
Right, of course.
Whether you can place them at the same time, or you can place them sequentially.
So there's two sills that they
So here they can be a sill complex that linked, and if you place them at the same time, you often get quite a substantial increase in the temperatures in between. Of course, if you let it entirely cool down, it will be quite different. But in this case, of course, and I mean, when you tweak it, you get a good fit here, basically, with between between the observations and the model in the 1D sense. It's the ball, but of course, again, the tweaking is, there are many variables to
Well, yeah.
parameters to use, but in that way.
TOC thing.
And what we do then, you know,
TOC is total
Organic
content.
Oh, okay.
And then, so if you look at this is from another paper, but the student at Ingrid Ornes did, but in a way, you look at the area covered by the sills, and then how much methane you can generate based on some different assumptions on the organic content, and for different number of sills. So basically here, just this Utgangssill complex was what we looked at. So that amounts to something like a few gigatons of methane that's been generated. If you look at the whole sort of ring and Møre basins, you get many thousands of gigatons of methane that can be generated in these soils.
But it's predicted. It's predicted.
This is, yeah, the predicted one, the model one, yeah. So we can, by putting large sill complexes into the basins, I mean, we can generate very large volumes of greenhouse gases. But the time scale, of course, is another issue. So how fast you do it, I mean, did this magmatism last for 10,000 years or a million years? It's hard to, we dated the one sill that we have with uranium lead, but we haven't drilled all the ones, so it still is a bit of uncertainties. What we realized with this, when we looked at the 3D data from TGS here and mapped it, we wanted for a long time to drill into one of these vent complexes to determine the age and what they look like. But they required a riser vessel, which is very, very expensive. But it was suddenly with the new data, we see a lot of these vents here, and they were only below 50, 60 meters of sediments, so they're possible to drill. And they sit in the same location. So here you see the sills, this is a paleosurface, and this is overburden sediments. So we collected some P-cable 3D data across it with the University of Tromsø. So basically, again, here you see this upper part of the vent, and then we see the sort of the pipe structures. We don't see the sills on this because it's only very shallow. We wanted in some ways to drill one hole through here, but the safety panel said no, for obvious reasons, that you don't drill a closure where you can have gas.
Right.
So we wanted to drill one borehole on the flank, very, very flank of the vent, and one as close as we could into the towards the vent itself, and then we drill 3 other holes just to sample the vent infill. So if you look at the scale here, this is 300 meters down below. You get beautiful cores from piston coring, but also from more sort of the or more hard rock coring. Here is a bit more biscuited, but still quite nice deposits. What we find in the vent complexes is this sort of Apectodinum augustum, which is a polynomorph that is very typical for the PTM, and it was very thickened sediments here. So the timing of this vent was the same as the PTM on a 100,000 year time scale. And we found other very immature microfossils. So it has never been deeply buried.
So why are those truncated? Yeah, that's actually what I'm kind of curious.
So this is sort of our interpretation here. The biggest unconformity here is this one. This is almost like a 50 million year hiatus between late early Eocene and Quaternary deposits. So something happened here. We don't have a good model for the doming. Something I definitely want to develop and something, but this is a late stage doming.
Yeah.
And this is also being very much truncated. So we have some PhD students that's working on the details there, but it's not been done yet.
But I mean, any idea,
Hmm?
like any hypothesis?
Well, initially when we mapped it out, we thought it was going to be basaltic massive rocks that caused differential compactions. And then we have some boreholes in one of them, and it says that it's undercompacted or a ballooning effect. It's perhaps so, then you may need to maintain high fluid pressures.
Okay.
But that we need to test. Or it's some sort of squeezing, you know, if you have something tectonic squeezing that the infill here is full of, is also full of a type of ooze, biogenic ooze, microfilm, that's
So
very,
ooze.
ooze, you know, so they also have different sediment properties within the eye structures and compared to what you have in the normal sediments around.
When that rift basin was opening, were there kind of salt, like saline deposits, like Red Sea kind of things that then redissolved deep or something?
We could have it here, Triassic salt. Or
Triassic.
very old salt, but it wasn't like a Red Sea basin then.
Okay.
So anyway, and also when you do all of the analysis here of the sediments, you find that you have large negative carbon isotope excursions. That's characteristic for these PTM. If you have marine sediments, it's quite big. If it's terrestrial, then normally is somewhat smaller. So this is sort of was one of the major findings for us from the expeditions, at least that we published, that these vents again, time-wise, they form that the PTM time in this way, and it sort of corroborates the hypothesis that these are linked processes. Also, that these vents were formed in shallow water, so the methane that comes out is not being dissolved in the seawater. So that was that part. I'm gonna do a little bit also just on basalt reservoirs, as this is more sort of close to what we are working on in this project. So in this case, you take carbon and emit it into the atmosphere from and you cause global warming. Of course, we then work on opposite problem in terms of taking carbon from the atmosphere and putting it into the basaltic rocks and making carbonates, not organic carbon. But so John Millett that works with Weber, he's compiled just a paper recently on the igneous reservoirs. I mean, sometimes igneous rocks are very massive and have no reservoir properties, but it's also quite a few places where you have permeability and porosity in igneous rocks. So it's petroleum related. Of course, it's also geothermal related, the big aquifers around in the world, where you store a lot of fresh water in these igneous rocks, like in the Columbia River, as you can see in this part here. And then you have for carbon storage, and that's sort of like with the Iceland Carfix project, very small projects, also with sort of gas project. We mainly worked in the Northeast Atlantic. We worked in the Deccan a bit. We've also done quite a few projects in Brazil and Paraná and Deca here. So in the volcanic margin setting, this is type of the scenarios where we look at where we can store CO2 in different type of reservoirs associated with volcanic rocks. So you can look for potential to store CO2 within the volcanic rocks themselves. So we need permeability and porosity in the rocks. We can look for potential to store CO2 below the volcanic extrusive deposit, below the lava. So then they could be a seal, or if you have leakage of CO2, they can react and in that way form sequestration. It could be like we talked about with the Rosebank in the west of Shetland. You find large petroleum accumulations in sediments between lava flows, but these can also be used for CO2 storage. We can have them in sills or below sills, or in ash volcanogenic type of sediments that's also reactive. So we look in different projects at these type of various reservoir styles. think I'll skip this. In the Northeast Atlantic, we have a combination of industry boreholes and of scientific boreholes. So that's a database that we are using to try to understand the reservoir properties of these type of rocks. So, yeah. And of course, partly what we did in our IDP trip was to try to drill more of these volcanic rocks and sample them, and using then the part not on these volcanic margins there to look for reservoir potential for CO2 storage. So for a large part, we have very good control on the distribution of the igneous rocks and the thickness of them. So this is just a top basalt map where we look at the thickness of the volcanics from the Vøring margin in Norway into the west of Shetland Basin. First place I'm looking at was the first boreholes. It's called the Kolga High. And here we have mapped the top basalt. So this is this reflection here. And we can map the base of SDRs in the west. Then we go further towards the east. We see this very well-defined progradational unit that we call the lava delta. We go into the sedimentary basins where we see the sills and these vent complexes. But we were very interested to drill this part here, which was basically a fairly transparent unit below the basalt. It looks like it's planated and eroded. And what we find here is granite. So it's and it's basically 700,000 years older than the basalt, and this was highly surprising in some ways. But we also then see that these lava sequences here, this is just a picture from the core, but it's sandstones in between the individual lava flows. It's a mixed sedimentary system where you have clastic input and a volcanic system. We find this in the Columbia River basalts also, thick, very thick sandstone units in between the basalts and elsewhere. So it's something that happens that you have problems. You have an igneous source and you have a sedimentary source.
Granite is only 700,000 years older than the basalt.
Yes, very enigmatic. I never worked a lot with granite, and we try to get in touch with people that knows it, because you need to form the granite, you need to uplift it and erode it.
Yeah, exactly.
And so how do you do this? First we thought that, okay, these are sort of like early Paleozoic, but Paleozoic related to the Calvinites or something like that. Yeah, but
that's very
it's still work in progress to say to understand. So this picture here shows basically, here's a seismic interpretation of the top basalt. So this is the top basalt horizon. But then you use look at the amplitudes and you blend it with incoherency. So this is just the top basalt horizon. So it's a very paleo landscape where you can look at the paleo environment. So here you see basically lava. It's a lava flows. It's a lava field. They're coming from the west, going to the east. And when they come to this sort of paleo coastline, they've been fragmented and they go down this kilometer-high escarpment as debris flows and deposited in the basin. So with this 3D data, you can get this amazing type of paleogeomorphology.
So the lava flow on the slope was meeting water.
It was this was a paleo coastline sitting here.
Okay, so when you see the flows, they look like the ones that are deposited in the water environment, right?
Yeah, so they become pyroclastites.
Like Hawaii.
Yeah.
So
Hawaii is a perfect example for this. I sometimes show a movie from the recent eruptions. I mean, the lava delta is the best described from Hawaii, from the Big Island. You can see here, but here you also then, this is a base basalt, and it forms this large scale dome. You look at the scale there, it's a closure of about 370 square kilometers. But here goes, it's just the different 2D profiles from the 3D cube. And you can see like here, it comes over this pre-existing dome and it builds out these lava deltas to the escarpment that you find here.
And the horizon is the base, right?
This is the base here. Okay. Previously, we looked at the top, so
Yeah.
the top,
Yeah,
but
yeah,
we can
yeah.
map the top and the base here with confidence on this data. So when we did the drilling, this is just the same cube, but we just look at it in a different way. So further west, so up here we got about 250 meters or so with sediments, and then you have the top basalt, and in this area here is very pitted, and here is very faulted. And it represents two different sequences of SDRs, basically. So these are lava flows, and we have the base basalts here. You can see it's faulted. So we drilled into this part and into that part. And then you get these extremely vesicular, very vesicular basalts, and none of the vesicles are basically infilled with alteration minerals. Sometimes there are, you get zeolites and carbonates and so on. So in this case, they were quite nice and open. So this is sort of the type of database that we have for the PadBas project to work with here, that we have about 100 meters of basalt penetrations and sediments in between, with a good suite of wireline log data and image logs and so on to characterize what could be the potential here. And this is sort of a small animation that John made during the cruise, if I get it to work. Yeah. So it's just like here you got lots of vesicles and they coalesce, so in that way you just they're just extraordinary permeable, on a local scale, of course. So that's sort of one end member that you just
I built a model like this, and I was wondering, what's the percentage of vesicles about? Is that like 30% or 20%?
Probably. They're quite high, but of course it's a very stiff rock anyway. But you can have
To get enough connectivity.
Because
I was trying to figure out how to set up a model, and I was doing like random distributions.
You see here, good. So this is John's plot again then. So porosity of about 30% here. You get the coalescence in these parts. So these are sort of, you go from the massive part to But of course, if you get secondary mineralization, it will decrease and so on. But in fresh basalts, you can get like up to 50% porosity. It can be extraordinary porous and permeable. So the basaltic rocks, and John's been spending a lot of time to gather then good databases from volcanic basaltic rocks with the porosity and permeability variations.
So, but the markers are coded by the borehole, or what? What is it? KMA1.
These are boreholes, yeah. These are from Hawaii.
Hawaii, so something
This is from
Iceland. Oh, and that's also the name of the facies type, right?
No, but this is Hoi Hoi or
Okay.
and transitional is a
So you have three different boreholes and three different types. Okay.
So different boreholes, different flow types, and so on.
I'm just wondering why all 16 samples that we got from the Skolka are so impermeable.
So it depends this you need to talk to John about,
Yeah.
So it's because it's a lot of variations and compiled a lot of parts there. So I just say that what we do in the PadBas is like building a database to characterize the sequestration sites. So 2D, 3D seismic, EM borehole data. We use Skoll as our primary part because we have a lot of data here. Rank of storage sites. Then it's like what IFE is doing in characterizing the fluid connectivity. And then we did a baseline 3D high resolution survey, and then the University of Tromsø also did a time lapse. So to look at the repeatability. So they also do OBS, And next year, the Germans are going back to this area to do electromagnetic also.
Who knows what OBS means?
Yeah.
So it's ocean bottom seismometers.
Yeah.
No, GIF is.
I forget sometimes.
Yeah, I mean, the presentation almost finished, right? But I still don't know what SDR means. SDR is.
Well, I have a separate slide on that in another part, but it means seabed dipping. It depends. It have 4 or 5 different type of
SDR.
Explanations, acronyms, but basically seabed dipping reflections.
Ah, okay.
So they're just from it's an observational thing, but they often used to be synonymous to basalt, subaerial basalt sequences, because that's what I think they are. So SDRs is what you talk about volcanic rifted margins. If the SDRs, these SDR packages are lava flows, which means that it's a volcanic margin. So it's used both as an observation and as an explanation. Typical science.
So when you say residual salts, the strontium isotope, is that residual salts meaning like dried out salts in the cores or
This I have not written.
Okay.
I'll be honest.
So it was. I don't know. Probably he was just grounded the samples and analyzed the content of the ratio of strontium, different isotopes.
No, yeah, I realized that. I was just wondering what the salts were.
Yeah, exactly. But what exactly he
out.
used for that, I don't know.
That's the thing we worked on with on the mid-ocean ridge basalts, the strontium isotopes.
Probably in carbonates.
So what we work on quite a lot then on So building earth models and doing seismic modeling is partly what we're doing, and trying to characterize the reservoirs is that's what we've been talking about. How well can we really determine from seismic data the reservoir characteristics, integrating observations from the field, borehole data, seismic data. And it's not a trivial thing to do, but it's but we can make models for it, and it's important, of course, from what you can do with the modeling and using it for input for that.
So how do we know how the colonnades are formed?
Yeah.
The colonnades. So what is it?
Shrinking.
Shrink?
Cooling, shrinking.
Yeah. It's the upper part is the entablature, and then it goes into the colonnade, and you get this.
This is the stuff as
So
Scotland. This
were they formed synchronously? The top part and the colonnade. Are they part of the same?
Top down, you're cooling from the bottom up.
Okay.
Usually those are kind of in the lower middle part of it.
So they're not different lava flows from different times. Oh, okay.
It can be the one is one flow, or it could be also in the sills, and they form during the solidification basically of the lava.
So how thick is it?
That would be 30 meters, 40 meters. Typically in reasonably thick units.
That's very thick.
But they also they say sometimes it helps to have a moist environment. But they form severely most of the times, but in a moist environment. So you see the top part of the lava flow here, it's very, very chaotic, whereas it's very well organized in the colonnade. It's and they typically are hexagonal, so you can find them on the wireline logs when you can. This is just my conclusion slide as I had in the beginning, so. So this was basically what we are working on. It's a synthesis of what we've done and what we're working on, that we have a lot of very good core data and data-rich province on the margin of that we are studying with students and collaborators like on this project here. So
All right,
That's
thank you. So we will start with questions here in the room if we have any. We will not shy of asking questions during the talk.
No, but
So, and
it is-
people online, can you please type in your questions if you have any, and we will then discuss that. Okay, anyone? No questions, but thanks for the talk. Yeah, it was impressive. So, if nobody has any questions, I have one. So, how many petroleum reservoirs, like commercially viable petroleum reservoirs, we have in basalts? In actual basalt rocks? Do we have many?
It's between, it's not many, but there are definitely quite a few. They're in Brazil, they're in the Ken Basin in Argentina, they would be in India, in the Deccan. You have them in the North Atlantic. Probably, and in other type of volcanic rocks, you would find them also in parts of different places in the world. But I mean, it's not the main target for any type of exploration companies, no?
Yeah. I mean, your company is called Volcanic Basin.
Petroleum energy research.
It
yeah.
used to be petroleum
Yeah,
research, right?
but-
So that's why I'm asking. So
It's a difficult, I mean, most petroleum companies, they don't like volcanic rocks, so they like to ignore them, and then typically they normally come to us after they're done drilling, you know? When they drill into the volcanic.
It's typically, the salts have a lot of scattering, and hard to see through.
Yes, so the top is, so for very long time, it was just seismic imaging, just to identify reservoirs. If you go to like the Brazilian margin, for instance, in the pre-salt, like Libreville, half of the wells in the reservoir sequence goes into volcanics. It's one of the larger petroleum fields anywhere, you know, so it's an integrated part of a basin. Almost, if you have rifting, you often have magmatism. That is, so most rift basins that have petroleum also do have volcanics in parts of the basin. Go to the North Sea, it's in the deep part. If you're in other places, it's in the entire part that you have it. So what we want to do is in a way is like we want to image the basalts, and then you want to have methods to identify them based on the seismic data, because so that reliable methods to interpret them. If you have good 3D data, that's nice. If you don't, it can be quite difficult. People like to see it. What's that? You know, is it you have a high amplitude reflection, and is it a carbonate or an anhydrite or a sill or lava? I mean, many times you cannot see. But,
So I have a question. How are you now kind of predicting permeability? You know, from seismic, and now you've drilled into these basalt. Because, you know, of course, there's fracture permeability, then there's permeability from like hyaloclastites or something, so they're different.
so for us, it's the way we assess it in this way would be initially to interpret different volcanic fascias. So you look for a reflection pattern. So I mean, if it's a prograde pattern, you interpret, you have a hyaloclastite. So then you need to go, how many wells do we have in hyaloclastites? Not so many. We can go to the field and then we find analogs. And then we compile the petrophysical data from boreholes that penetrated and from field data.
So
then we can assign some petrophysical properties. But then we come into what you showed in your presentation too. So we need to then also have some large scale fracture network on top of it. And that can be, then you can interpret, like in the skull that I showed you, we have faults that cut through, so we can map them, but other places we don't. So this is a part of you need to use a combination of interpreting fascias from science, borehole data, field data, and integrate it.
So you're really using the geology rather than using like a direct, a geophysical.
Now, it's very difficult to do it directly
Right.
because, like you say, in a sense, the range of velocity in the basalt goes from 2 to 6 kilometers per second, and depending on the alteration stage, depending on the burial depth or the circularity and so on. So it's very difficult even if you take just the seismic velocity to transfer it to any type of reservoir property.
Are you trying to move in that direction? So now you have core and you have seismic data, so you can use some direct petrophysical measurements as opposed to inferred petrophysical measurements. Because, like you mentioned, even in a single lava flow, you're gonna have orders of magnitude difference in permeability. And like, I find it like hard to believe that you can like really extrapolate like from measurements of one lava flow and say like, oh, well, this one that we see in the seismic data maybe has similar, it's hard, I think, to have a lot of confidence in the estimation of the extrapolation of those petrophysical measurements, but you have core from the actual places. Have you started to make some more concrete links between the geophysical data that you have and the petrophysical measurement of the core?
Yeah, so we make models. So we started running a bit of the seismic modeling for this, both in a 1D, 2D sense in a way. So that is a part of the link, but it's yeah.
So porosity and fracture density, for example, it's something that appears maybe feasible to predict based on geophysical data, right? But the permeability, I mean, the plot that John Miller put together, right? Where you have this threshold 30% porosity, and if you have 29, it's 1 microdarcy. 31, you have
I guess
100
when I see a plot,
millidarcy.
like if you saw that plot without any of the lines written on it,
Yeah, you wouldn't see the
doesn't
threshold.
really. I'm not sure I would pick that 30% threshold. It looks like a big
That's
square
that's
to me.
That's why you're not a petrophysicist.
No, I guess.
Yeah, and then you have the secondary mineralization line, another thing, right? It collapses everything.
So it's probably quite a bit to learn from hydrogeology too, because for sure, like in many places, like in India or in the Columbia River, they have a lot of boreholes and they produce a lot of water from this.